Today, I'm going to explain the topic histogram equalization in digital image processing. This technique is commonly used to improve the contrast of images and make details more visible. In this presentation, I'll be explaining what a histogram is, the principle and mathematical concepts behind histogram equalization, such as PDF and CDF, and how the transformation function enhances image quality. I'll also demonstrate this process using a Python program and show how the results clearly improve the image's contrast. Let's begin with a quick introduction. Histogram equalization is a contrast enhancement technique widely used in digital image processing. Sometimes, when we capture an image, it might look too dark or too bright. This happens because the pixel intensity values are not spread out properly. Histogram equalization helps to redistribute these intensity values so that all gray levels become more balanced. As a result, the image looks clearer and more detailed. This technique is simple yet powerful and is used in areas like medical. Before understanding equalization, we must know what a histogram is. A histogram is a graph that shows how the pixel intensities are distributed in an image. On the x-axis, we have intensity levels ranging from 0 to 255, where 0 represents black and 255 represents white. On the y-axis, we have the number of pixels corresponding to each intensity level. If an image is dark, most pixel values are near 0, so the histogram is concentrated on the left side. If it's bright, the histogram shifts to the right. For good contrast, we want the histogram to be spread across the full range, and that's exactly what histogram equalization does. The main principle behind histogram equalization is to flatten or spread out the histogram. This means that we try to make all intensity levels occur with approximately equal probability. When we apply this technique, it adjusts the brightness and contrast in such a way that dark regions become brighter and bright regions become more balanced. This increases the dynamic range of the image, which means more visible details in both shadows and highlights. So, in simple terms, histogram equalization transforms the image so that the intensity distribution becomes uniform, resulting in a visually improved image. Now, let's look at the mathematical part of histogram equalization. This process involves three main steps: PDF, CDF, and transformation function. PDF, or probability density function, is the ratio of the number of pixels at each intensity level to the total number of pixels. It is given by the formula P, RK, equals NKNP, RK, equals NNK. Here, NK is the number of pixels with intensity RK, and N is the total number of pixels. Next, we calculate the CDF, or cumulative distribution function, which adds up all the probabilities up to a particular intensity level. It is represented as Sk equals the sum from j equals 0 to k of p of rj. The CDF helps us understand how the intensity levels accumulate across the image. Then we use the transformation function, ska jal arns L1 andis ka, where L is the total number of gray levels, usually 256. Finally, each pixel in the original image is replaced by its corresponding new intensity value, Sk prime. This gives us the equalized image with better contrast. In this slide, I'm demonstrating the manual process of histogram equalization using a given data set of gray levels and their pixel counts. We start with a table showing the original gray levels from 0 to 7 and the corresponding number of pixels for each level. The first step is to compute the probability density function, which is found by dividing each pixel count by the total number of pixels in the image. This gives us the probability of occurrence for each intensity value. Next, we calculate the cumulative distribution function, which is the cumulative sum of the probabilities up to each gray level. The CDF represents how intensity values accumulate across the image and is the key part of the equalization process. We then apply the transformation function, which is Sk equals open parenthesis L minus 1 close parenthesis times CDF open parenthesis RK close parenthesis, where L is the total number of gray levels, which is 8 here. This gives us the new gray level values after equalization. After rounding them off, we obtain the new mapped gray levels for each original intensity. Now, We create a new table showing how each original gray level is mapped to its new gray level, along with the number of pixels. From this, we can observe that some gray levels are merged and others are spread out. This indicates that contrast has been enhanced. Finally, the last graph shows the equalized histogram, which is more balanced compared to the original one. The pixel values are now more evenly distributed across all gray levels, showing that the image's contrast has improved. Now let's look at how histogram equalization actually enhances an image. On the left side, we can see two images, the original one at the top and the image after applying histogram equalization at the bottom. The difference between a low-contrast image and its equalized version is very clear here. After equalization, the image looks sharper and more detailed. It reveals finer features that were hidden in the darker or brighter regions of the original image. Basically, histogram equalization spreads out the intensity values evenly, so the contrast becomes more balanced across the entire image. Here's the Python code used to perform histogram equalization. We first import two libraries, OpenCV for image processing and matplotlib for displaying images and histograms. We read the image in grayscale using cv2.imread. Then we apply cv2.equalize, hist open parenthesis img close parenthesis, which automatically performs histogram equalization. Using matplotlib, we display the original image, equalized image, and their respective histograms side by side. When you run this program, you'll notice that the histogram of the equalized image is more spread out, and the image itself appears much clearer. Here's the same code that I executed in Jupyter Notebook. This demonstrates how histogram equalization enhances the contrast of an image effectively. Here are the final results. Before equalization, the image had poor contrast and appeared dull. After equalization, the image looks brighter, with details visible in both light and dark areas. The histograms clearly show the difference. The original histogram is narrow, while the equalized one is spread over the full range. In conclusion, histogram equalization is a simple yet powerful technique that improves image contrast by redistributing pixel intensity values. It is widely used because it is easy to implement and gives visually significant results. Thank you for listening. Let's summarize the key takeaways from this topic. First, histogram equalization enhances contrast. It improves the visibility of details by redistributing the brightness levels of the image. Second, the whole process relies on the concept of the cumulative distribution function, or CDF. This mathematical function helps in mapping the original pixel values to new ones in a way that balances the overall intensity. And finally, this technique has broad utility. It's used in many fields like remote sensing, biomedical imaging, and pattern recognition, where improving the quality and clarity of images is very important. In short, histogram equalization is a simple yet powerful method for image enhancement.